All right, so thank you for the kind introduction. So I'm AJ, and I'll be presenting our work on Bonsai, a compiler for queries to prune tree traversals, and this is joint work with my lab mate Chris, our advisor Fred, and collaborators at Stanford, MIT, and Adobe. I want to motivate with a simple motivating example of a range query, which is a fairly standard database operation. I have a set of numbers illustrated here on a number line, and I want to collect all of the values in between some low value and some high value. This query can be accelerated a number of ways, and via a number of different tree types, but I'll illustrate this example with an interval tree. So I can, and in Bonsai we represent this via a simple filter over a set of integer values x, and we select elements from that set between low and high. Via an interval tree, we can accelerate this query by recursively constructing intervals that contain the subtree, the values of the subtree beneath them. And we can accelerate the range query by slicing this interval tree via the low and high interval values. In functional notation, this gets lowered into a tree traversal over an algebraic data type tree, where when we match on the tree type and we see a leaf variant, we evaluate the filter predicate, checking if x is within the range, yielding the singleton set x if x satisfies it, and otherwise an empty set. For an interior node that stores a left and a right subtree, as well as an x low and an x high value, we first check whether or not the filter predicate is always true, which is true when x low and x high are fully contained within the query interval. And if so, we scan the subtree T. Otherwise, we check the case where the filter predicate is maybe true, and we union the subtree results, the recursive results of the left and the right subtree. If the filter predicate is not always true or maybe true, it is never true, in which case we return an empty set and we don't recursively visit the subtree. For the tree on the right here, the root node lies in the maybe case. The interval at the root node overlaps with the query interval, and so we recurse into the left and the right child. The left child hits the always case. The AD interval is fully contained within the low to high interval. And so we can scan that subtree without needing to reevaluate the filter predicate on the remaining, the left and the right subtrees of the green node. And lastly, the right subtree of the root hits the always case. This interval does not overlap at all with the query interval, and so we can prune this node. And this is the sort of general structure of using a tree to accelerate a query, specifically like an augmented tree. But filters and range queries are not the only things that you can accelerate. So suppose I wrap the filter in a count operation, which is fairly standard in a database system. We can take the structure of the filtered traversal and use it to compute the fuse result of the count of the filter. And so what that looks like here is we change the return type to be a simple integer value. We change the leaf case to return 1 if the filter predicate is satisfied and 0 otherwise. The scan case actually counts the size of the subtree. The former union actually takes the sum of the two subtree results, and returning an empty set returns 0. And this is how you perform a fused operation on a tree. But counts and filters, or counts and range queries are not the only operations that we care about accelerating via trees. And in Bonsai, we support count and a more general notion of filter, as well as any and all, which are sort of binary forms of filter, a more general form of reduction operator for associative and commutative reductions, as well as idempotent operators like argmin, argmax, min, and max. We also support product, which is going to allow us to represent an interesting class of joins. And while we have sort of sub-languages for expressing the metrics for argmin and max, I'm not going to talk about that today. So if you're interested, look at the paper. But I will talk about our predicate language, which supports Boolean combinators, arithmetic combinators, as well as geometric combinators. So we can check whether one geometry contains another, or a geometry intersects with another, and so on and so forth. And this is going to let us to represent some really interesting algorithms from the spatial query community, including ray tracing, closest point queries, and collision detection. And so Bonsai takes this high-level query specification, as well as an algebraic data type representing the tree data structure, with explicit annotations. And those annotations look like tagging data, scalar data, to be within a low and a high value, or tagging geometric data to be within a bounding volume, for example, an axis-aligned bounding box. But it also looks like more general reduction operations, like storing the count of a subtree or the minimum ID of a subtree in fields C or M, respectively. And Bonsai takes these two specification languages and compiles to a tree traversal IR that enables us to do efficient fusion of the operators, as well as a technique we term predicate analysis, which is all about taking this predicate sublanguage as well as the bounds annotations and generating these always, maybe, and never conditions that I showed on the previous slide. And then we compile to C++. So that's sort of the high-level overview. And before I get started talking about fusion and predicate analysis, I want to talk about what the state-of-the-art in generating tree traversals is. And this is a bit of a misleading slide, because the state-of-the-art before Bonsai was that you write your own. If you have some set of queries that you want to implement, or even some fused set of queries, before Bonsai, you had to implement that set of queries times every single tree that you want to use in your database management system or other accelerated query system. Bonsai's techniques enable linearizing this dependency, so you can now write a batch of queries a single time and a tree specification a single time, and Bonsai handles this quadratic dependency for you. And so what that looks like is we take our high-level range query expressed as a filter here, as well as a declarative tree specification for implementing the integer set. And so that's shown here. The type tree has two variants, a leaf node that stores integer data, and we explicitly tag that data as data to be represented within the set. And an interior node, a recursive variant that stores a left and a right subtree, as well as this x low and x high value, with data explicitly tagged to be within that scalar range. The Bonsai compiler is a bottom-up code generator. And so we take this tree specification and we take this query, and we first generate a base iterator for the base set. And so to iterate the base set, we produce the following tree traversal, which matches on the tree type. For any data, for any variant with an explicit data label, we yield that data. And for any recursive node, we scan that subtree. If we want to take this base iterator and generate the filter that I showed previously, we simply rewrite the yield of x to be guarded by the filter predicate, and we rewrite the scan of the subtree t to be wrapped in an always condition for the filter predicate, or in the case of the maybe condition being satisfied, we union recursion on t. Otherwise, if it's not always true or maybe true, it's never true, and we return an empty set. For this particular example, the range query, the always and maybe conditions are exactly the interval containment and overlap, respectively. And so the Bonsai compiler stamps in those conditions. Now, if we want to, once again, implement the count of this filter, we can apply small local changes. First, we change the return type. We rewrite yield to be 1 or 0. We rewrite scan to be the count of the subtree, and we rewrite the recursive union to be the recursive sum. And then lastly, the empty set becomes 0. But we can actually accelerate this query even further with Bonsai's machinery, which is if we extend the interior node to additionally support account augmentation, shown here, we can rewrite the always case to, instead of recursively count, we can just return that memorized value. And hopefully the intuition I'm giving you here is that fusion in Bonsai is a simple local rewrite of yields, scans, and froms. And that is exactly how the code generator is structured. So we iteratively rewrite these yields, scans, and froms. What the rule for lowering a filter of an arbitrary predicate P over a set S looks like is we first lower the generator for the set S, and we rewrite any yields in that generator to be guarded with the predicate P. Similarly, scan gets guarded with an always P predicate. If we can't prove that the predicate P is always true, then we check if it's maybe true, and we union the subtree results, otherwise returning the empty set. And then union froms do not get rewritten. We could implement a similar lowering rule for count, and I show an example of that here, which applies the same rewrites that I showed you on the previous slide. However, that would be a little bit misleading because count is actually expressed in Bonsai as a sum reduction over the map from an element to 1. And I don't have time to talk about all of the different rules in the paper, that we show in the paper, but we include rules for all of the different operators that we care about. And this is how we achieve fusion. Now, the way that we choose that we achieve pruning is via the generation of these always, maybe, and conversely never conditions. And to do so, we take some insight actually from the Halide compiler, which performs rather extensive symbolic interval analysis. And we realize that an always condition for a predicate P is the lower bound of the predicate, and a maybe condition is the upper bound of a predicate. You can also think of these as necessary and sufficient conditions. And Halide generates necessary and sufficient conditions via symbolic interval analysis, and we do the same. So we can apply rules like shown on the right here, where the lower bound of A and B is the lower bound of A ANDed with the lower bound of B, and similarly for the upper bound because AND is monotonic in its arguments. And so that gives us the first step in generating always and maybe conditions for this particular predicate. And we can similarly apply rules for A is less than or equal to B to generate the next step of lowering always and maybe. And now we've sort of hit some base cases. So the upper bound or lower bound of L and H these are non-varying values, and so they are just L and H. The upper bound and lower bound of X is actually given via our algebraic data type annotations. And so we can generate these pruning and inclusion conditions via the bounds annotations on the algebraic data type. And sort of the sort of key insight here is that these pruning conditions can be generated via symbolic interval analysis, and we call this predicate analysis. The results of pruning and fusion are that we get asymptotic speedups over sort of like linear scans, which is the existing alternative if you don't have a tree accelerated data structure for these queries. So on a number of filters, we evaluate on varying problem sizes on the x-axis, and we show the speed up over linear on the y-axis, and both of these are log scale. We show that we get rather massive speedups over linear scans on a variety of filters that database management systems fail to map to tree queries. But you'll see that there's sort of a tapering off at a certain point. And that's because these filters are not very selective. And so the runtime becomes write bound, where they are writing large amounts of outputs. And so to make these queries no longer write bound, we can instead query the count of the filter, where we're just accumulating the sum of the count. And we see that we can lift these speedups up even further. But there's still a tapering off. And that's because these queries have become read bound. They're reading too much data, and we get memory bound. However, if we extend the tree data structure to have the count augmentation of the subtree beneath it, we get near perfect asymptotic speedups for all of these queries, whether they're selective or not. And in the paper, we include a fusion ablation, as well as more advanced multidimensional filters and reductions and joint evaluations compared to database management systems. But with my remaining time, I want to talk about the exciting extension to predicate analysis, which is geometric predicate analysis. We started this project with the intent of accelerating queries like ray tracing and collision detection. And so there was always sort of an intent that this would be sort of a spatial query compiler. And I hope to motivate that with a sort of a simple extension to the range query example, which is suppose I have 2D space and I have a bunch of points in 2D space. And instead of selecting in a particular range, I want all of the points contained within a circle. In Bonsai, you can once again represent this as a simple filter over a set of objects such that a circle S contains the atoms of that set. And I can similarly build a tree on 2D space, wrapping points in bounding volumes recursively until I construct an entire tree. And then I can once again recursively evaluate on this tree, where yellow represents the maybe case, and green represents the always case of the filter predicate being true, and red represents pruning. So now you might say, well, okay, how do a predicate analyze contains? And if you're familiar with geometric implementations of circles and points, you might say, well, just unwrap the implementation of contains and apply symbolic interval analysis to that. And that would actually work for circles and points. However, real-world geometry is considerably more complicated than circles and points. So suppose my base objects were actually triangle meshes. The implementation of whether a circle contains a triangle mesh is shown here. It's not important that you understand it. What is important is that you see that there's control flow, and it is non-trivial to analyze. And in fact, if you apply symbolic interval analysis to this, you actually get almost a nonsense result out of it that never prunes anything. And so we argue in the paper that for non-scalar operations, you need a reason explicitly about the operation semantics and not the implementations. And you can do so for all of these geometric operations. So for example, if I want to lower bound whether a geometry S contains a geometry X, the geometry S absolutely contains the geometry X if S contains the bounding volume of X, and that's because containment is transitive. Similarly, if I want the upper bound of whether S contains X, then that is that S intersects the bounding volume of X. And the intuition behind that is that if S does not intersect the bounding volume of X, it simply cannot contain the geometry X. And we include a number more geometric rules in the paper. The interesting results of these geometric extensions are what we like to term representative power without sacrificing performance. And what that representative power looks like is that I can implement ray tracing via 3 lines of code, maybe 2 if you have a longer code editor. I can implement closest point queries via a simple argument, and I can implement collision detection via 2 operations, the filter of a product. But the important thing about this representative power is that we do not sacrifice performance when compared to handwritten, hand-optimized code. So when we evaluate ray tracing versus the FCPW library, where orange is FCPW and blue is Bonsai, we get near exact parity. In fact, sometimes a little bit faster. This is showing runtime, not speed up. Similarly, for closest point queries, we get near perfect parity with a state-of-the-art library. And for collision detection, we actually see about a 1.5x speed up over the flexible collision library. We checked. This is not actually better pruning. It is that they have a slightly worse implementation, but not for pruning purposes. And with that, I'd like to leave you with the overview of the Bonsai compiler and a quick shout out that Bonsai is actually not alone, and it's part of a bigger system. So my co-author, Chris, presented Scion yesterday, which is all about extending the Bonsai project to have a physical layout memory specification language, which lets us truly get a really peak performance for these spatial queries when compared to the state of the art, and achieve data independence for trees. So unfortunately, due to the ordering of conference talks, this talk was yesterday. But if you're interested, I encourage you to read the paper or watch Chris's the YouTube talk. And I'm happy to take any questions.
All right, again, so we'll take questions at the mics. Yep, Gilbert, one.
Thanks, this was really cool to see.
Thanks, Gilbert.
Oh, Gilbert Bernstein, University of Washington. Thanks, Pavel. 2 questions. Does it work on GPUs? And does it support any building of the tree hierarchies?
Excellent questions. So yes, it works. So Bonsai does not evaluate on GPUs. Scion does evaluate on GPUs. It's the same system. We evaluate on NVIDIA GPUs in Chris's paper. You're probably going to ask if we target the ray tracing cores as a follow-on. We do not. That would be possibly interesting follow-on work. And then, sorry, what was your second question?
But it does evaluate.
We do evaluate on GPUs.
Oh, cool.
Yes.
The second question is, can you do the tree builds?
Oh, yes. So neither Bonsai nor Scion implements interesting tree build algorithms. For comparison to the state of the art, we implement the exact same tree construction algorithms that they build, because the tree construction algorithm heavily impacts the performance of ray tracing code. We do think that's interesting future work to explore the domain space of build algorithms.
Cool.
Yeah, thanks.
Okay, so I'm going to ask Justin to be the last question. Sorry if you could keep it offline. And James, do you want to swap with AJ?
My email is on the slide if you want to send me an email with your question.
Thanks for the lovely talk. This is Justin Lubin, UC Berkeley. A question that I had is, does the lower bound and the upper bound for the contains operator fall out of some other definition, like automatically, or was that something that you specialized for the geometric containment?
So that's an excellent question. The honest answer is that I thought really hard and came up with rules that seemed right and derived the state of the art in tree traversals. Collaborators who are significantly better at formal verification than me have since proved all of these rules to be correct. They have in fact found that some of the rules are not the tightest rules that they could be, though, so they can be optimized even further. But they are all correct. So
Thank you.
Yeah.